Hello everyone, my name is Yuze Zhang. So today I will talk about transport properties of non-reciprocal one-dimensional quantum channels at denser aluminum oxide and strontium titanate oxide interface. So firstly, I will think about our group and especially my advisor Jeremy Levy and Patrick Irwin. So for this interesting heteroxide oxide, it was combined by two insulators, the Ru and Stu. But when they combine together, there comes out a two-dimensional electron gas, and it becomes tunable. It could be tuned by a voltage, and then it can change between the metal and insulator. So we want to do some quantum simulation on this interface. Now we use the atom force microscope lithography technique. And so in this technique, we add a voltage on the tip. It actually leaves some protons on the interface, and then it could be conducting. And if we want to erase the conducting areas, we could add a negative voltage. It's just the deprotonation. So it comes out barriers. And these two steps could all both be repeated. And then when we try to see some transport properties, there comes out some phenomena. Firstly, if we got a single electron transistor, we could see the electron pairing without superconductivity. And also, it also has got the tunable electron and electron interactions. And today we will especially talk about the electron waveguide on this interface. So for this ballistic quantized transport at this interface, we will write a main channel with a length around 1 micrometer and use two transparent potash barrier to cut it. The length is around 10 nanometers. And then we could tune it by side gate. So then we can do some research and to see its some properties. Now you can see there's some quantization of the conductance. It's a Lander quantization. And also, if we write some different structure of the waveguide, such as a vertical, a lateral, or combine them, then we can see some rich subband structure on the transconductance figures. And also, this is the representative wave functions for these waveguides. So these are some formal work done by our senior students. So this is just a street waveguide, and if we want to write a interesting some different waveguide, we could do a modulation like lateral slalom motion. It could be reached by tracing a sinusoidal path with the tip. And also, if we want to get a vertical modulation, we could just change the tip voltage to reach that. And also, we could combine these two, get a helical modulation. And for this modulation, we can see it should has non-reciprocal properties. So these are some figures about this waveguide. We could see some new different band structures in transconductor figures. We can compare it to the straight waveguide. And especially for the helical superlattice device, we could see from the conductor figures there's some fluctuation around the plateau. It's very interesting, and it may be correlated to the spin orbital magnet combined with the magnet we given, and that's some work. So by the way, we find a paper. It talks about the chiral-induced spin selective effect, and this effect could cause the reduction of elastic backscattering in electron transfer through some non-reciprocal molecular. So we want to see if also there's some reduction of the backscattering in our non-reciprocal waveguide. So we design this device. We would like to combine a sine wave and two inverted quarter arcs into a non-reciprocal waveguide, and then we could repeat it several times to form this superlattice, and these are some parameters. So by developing this just a nanoscale platform, we could engineer some wires and do some research and find some transport properties, and it shows some oscillation transport behavior on the helical waveguide, which indicating the spin orbital indication. And these experiments and our future work is just a first step toward the engineering quantum wires, and we want to build a block. We want to get it as a building block in the future. In the future, we could research more.